Section 5.4 is the area and the fundamental theorem of calculus. So what are we going to be looking at? We're going to be looking at the area underneath curves, which turns into definite integrals, the fundamental theorem of calculus, marginal analysis, and how to find the average value of a function. It says, from your study in geometry, you know that the area is the number that defines the size of a bounded region. For simple regions such as rectangles, triangles, circles, area can be found using geometric formulas. For instance, a rectangle, the area is length times width. A triangle is 1/2 base times height. Circles were pi r squared. These are all formulas you learned back in elementary school, probably saw again in middle school, maybe again in high school, or even in a prerequisite course for this course. It says in this section you will learn how to use calculus to find areas of non-standard regions, such as the region R shown in the figure below. So the cool thing that we're able to do now is we've only been able to find areas of very specific figures, rectangles, circles, triangles, for instance, very geometric shapes. We've never been able to find the area of any shape. And for the first time ever in your college or in your mathematical career, we're going to be able to find the area of any shape. And so, for instance, look at this blue shaded region from A to B underneath the curve of f of x, y equals f of x. They call that region R. So how do we find the area? Well, they're going to use what's called a definite integral. You'll see why very shortly. It's the integral, the way that we would read that is the integral from a to b of f of x with respect to x. So it looks exactly like the indefinite integral. The only thing is you have two new things. You have a, which is called your lower limit or your lower limit of integration, and you have b, which is your upper limit or your upper limit of integration. So A is always the first point, B is always the second point. So what this indicates to us looking at this is I want to find the area beneath the curve. The curve is called f of x, and I want to find it from the interval a to b. That's what the definite integral means. So let's look at the definition right here. It says let f be a non-negative and continuous. We're going to be going with this non-negative. What non-negative means is it needs to be 0 or positive. So right now we're not doing anything below the curve. All the functions we're looking at have to be above the curve. We'll look at below the curve later on. So it says and continuous on the closed interval a to b. The area of the region bounded by the graph of f, the x-axis, and the lines x equals a and x equals b is denoted by, and it says the area equals, and again, here's the important part, the integral from a to b of f of x dx. So again, that's just saying find the area beneath the curve of f of x on the integral from a to b. It says the expression, the integral from a to b of f of x dx, is called the definite integral from a to b, where a is the lower limit of integration and b is the upper limit of integration. So let's look at an example. It says evaluate the definite integral using a geometric formula. Illustrate your answer with an appropriate sketch. Find the integral from 0 to 3 of 4x dx. So again, what they're asking us to do is look at the function 4x, look at it above the axis, on the interval from x equals 0 to 3, find the area of that shape. So we're going to try doing it right now without doing any calculus, just looking at the actual graph. So go ahead and use any graphing utility that you have. You can use Desmos is what I'd use in graphing, or quite simply, in all honesty, this is not a difficult graph to graph. We're graphing y equals 3x. So anytime I'm asked to graph something, I just plot numbers. So here's x, and then to find the y value, we're going to do 4x. So I'm just going to plot in numbers. I need numbers from 0 to 3. So let's play plugging in numbers 0, 1, 2, and 3. Let's find some y values here so we can actually graph this graph accurately on the interval from 0 to 3. I'll go ahead and label those 0, 1, 2, and 3. So there's my x-axis. So the question is what are my y values? These are pretty easy to do in your own head. If it was more difficult, I would use a table feature on my calculator. Remember how to use the table feature. Check previous notes how to do that. 4 times 0 is 0. 4 times 1 is 4. 4 times 2 is 8. And 4 times 3 is 12. So it looks like I have y values all the way from 0 up to 12. So I'll cut that in half, call that a 6. Cut those in half, I'll do a 3, and I'll do a 9. I just want to make sure my scale is accurate. Again, notice the x-axis and the y-axis don't need to match here. I'm just sketching a rough graph here. So I know one of the points is 0, 0. I know another point is 1, 4. That'd be approximately right there. Another point would be 2, 8. That'd be approximately right there. So I'm plotting my points and I'm labeling them in 3, 12. Plot that up there. Here's the point 3, 12. And so here's the line y equals 4x, but we only care about it on the interval from 0 to 3, so I'm actually going to stop at that point 3, 12, do a hard stop. So what are we looking for in this graph? What we're looking for is the area beneath the curve but still above the x-axis. The area beneath the curve but still above the x-axis. So as you can see, I'm shading that in now in blue. It's saying what's the area represented by this picture right here. I'm going to go ahead and close off that area, and I want you to notice the shape that it makes. The shape that it makes is a triangle. So I want to remind you that the area of a triangle is equal to 1/2 base times height. So let's think about it. What's the base of this triangle? Looks like the base of this triangle has length 3. And what's the height of the triangle? Again, we want to look at the y value here. The height of this triangle is 12. So if I want to find the area of this figure, I'm going to do 1/2 times the base, which is 3, times the height of this triangle, which is 12. So 1/2 times 3 times 12, plug that into your calculator if you need. I'm getting an area of 18. Now there are no units. Remember, area would always be units squared, but because we're just graphing it on the x and y axis, there's no official label to the units, but the answer would be 18 units squared. So what's the area beneath 4x but still above the x-axis on the interval x equals 0 to x equals 3? The answer would be 18.